All right, so now that we know a little bit more about time series noise and how that comes about, what we have to do is learn more about the actual properties of time series. And this is going to take us into the ideas of autocorrelation and autocovariance, which is going to be a really key part of everything we do in this course. We're also going to be looking at the idea of stationarity, because as much as time series move around, they actually stay kind of the same as you go throughout the time. So let's take a look at that in more detail.
All right, so welcome to Time Series, Stat 479, lecture number 2. Today we're going to go a little bit deeper into understanding different types of time series by their properties. So last time we mostly just focused on different types of processes that we might see. Things like the autoregressive, the moving average, white noise, Gaussian processes, linear processes. These are all the different tools that we'll be working with. And in this lecture, what we'll be doing is going a little bit further and investigating properties of time series and estimation in time series context, because, right, this is a stats course, so we want to actually estimate things rather than just understand their properties in some abstract sense. So the first thing that we'll be talking about today is autocovariance. So let's start with that. Autocovariance. So the first thing we need to think about is, well, what's the covariance, right? In probability for x and y random variables, right? What we have is that the covariance, the cov, between x and y, two distinct random variables, is going to be the expectation of x minus the expected value of x times y minus the expected value of y. It's a terrible y. Let's do that better. There we are. So we have this definition. Of course, the covariance of a random variable with itself is just going to be the variance of that random variable. And the idea is that the covariance is going to, in some sense, measure the linear dependency, which is not the right exactly way to say it, but the linear relation between these two random variables. So if we were to collect data x and y from my hypothetical example here, and if they had a positive correlation, or if the covariance were positive, or the correlation for that matter, which is just the normalized covariance, then we'd have something that looks like this, right? This would be positive covariance, and if it's negative, then it'll be sloping downward. If there's a zero covariance, then it's just going to look kind of circular. Of course, as I mentioned in the last lecture, and I'll more formally highlight here, that if the covariance of x and y is equal to 0, this does not imply independence. That's a common mistake that people make. But the reverse implication is true. Independent random variables do have a covariance of 0, but covariance of 0 does not imply independence. It only works in the Gaussian case. So x, y jointly normal. The joint normality is important here, because you could have two normal random variables that have some weird relation between the two of them. But if we have x and y being jointly normal, and the covariance between x and y equaling 0, then we have independence. So very good rules to be aware of. We talked a little bit about this when I mentioned Gaussian process in the previous, or Gaussian white noise in the previous lecture, right? Because when we go through our tiers of white noise, we have our uncorrelated white noise, which is the weakest. We'll start at the bottom. Then we get to the next strongest, which is IID white noise. And then the stronger than that is the Gaussian white noise, because the Gaussianity and the uncorrelatedness immediately implies that they're independent. It's independent as well. Okay, so we have this idea of regular covariance. So then what's autocovariance? Well, if we consider, again, we'll say consider a time series xt, which is again just going to be some random variable indexed by time. I'm not going to discuss, we don't have a specific form, but you could think of it as anything we talked about in the last lecture: a white noise process, an autoregressive process, a moving average process, or something else. Maybe there's a drift term, whatever you like. But we just have some hypothetical time series xt, and then we can define the autocovariance to be the covariance of, well, what we use is the notation k sub x at times s and t. And what this is going to be is the covariance, not the cosine, the covariance between the process at time s and the process at time t. Okay, so it's really just the covariance of a process with itself at two different time points, and hence autocovariance. Okay, so one, why are we using the notation k? Well, this can be thought of a little bit like an integral transform or a kernel function. So, I'll say in quotes here, k for kernel. It's not going to be overly relevant to what we're doing right now, but the idea is that you can think of it as a kernel function, which could be used for an integral transform. But we'll save that for later. There are some interesting properties here. Let's say properties of I'll just say kx, so I don't have to write that all out again. The one is going to be symmetry in the arguments. So what that means is that the autocovariant of ST is going to be the autocovariance at TS, right? This is just because multiplication is commutative, right? A times B is the same as B times A. And furthermore, if we just go up to this definition of covariance at the top of the screen here, what we have is that the covariance is just the expectation of the product of X and Y after subtracting the mean. So similarly down here, I can flip the order. It doesn't matter. It's symmetric. Furthermore, it is positive, possibly semi, or just positive definite or positive semi-definite. So what does that mean in terms of a kernel function? Well, in this case, or a autocovariance function, I guess, in this case, it means that for any finite collection of time points, times being, let's say, t1 through tk, right? We have that the k by k matrix, that the k by k matrix with, we'll say, ijth entry being right, k. Oh man, I'm reusing k twice. All right. well, emphasize that I mean little k for the dimension of the matrix, and big K for the little k for the matrix, and big K for the kernel function. Sorry about that. But what we have here is we have a Ti and a Tj. So you can imagine that what I have here is a big matrix with entries that happen to be this kernel function evaluated at Ti and Tj for the ith row and the jth column, right? And then this is just a big matrix. So if we write out this matrix for any finite collection or set of time points, then what we get is that, I'll say then, this matrix is positive, again, possibly semi-definite, depending on the setting, usually positive definite, if everything's kind of working nicely. So this is the way that we can extend the idea of a positive definite or a positive semi-definite matrix into a autocovariance function, which could be, in this case, indexed on infinite timescales. It could also be sort of on continuous time, but again, we'll be dealing with discrete time for the sake of this course. Now, just to make sure we all remember, right, little side note, note a matrix M is positive definite if for all x, vectors of the correct dimension, so that this actually makes sense, for all vectors x not equal to the all zeros vector, then we have that x transpose, let me think, yeah, we want row. So capital T, x transpose mx is going to be greater than 0. And if I put in a positive semi-definite, then I'm just making this greater than or equal to 0. And alternatively, right, a positive definite matrix means that its eigenvalues, symmetric positive definite matrix is one whose eigenvalues are all positive. With a semi-definite, you might have some 0 eigenvalues in there, or I guess you would if it's strictly semi-definite, depending on exactly how you pedantically define it. So it's just a nice property, and it's something that we know about covariance matrices. Covariance matrices in multivariate statistics have to be positive semi-definite, much like how a variance has to be a positive number, right? The positive definite matrix is kind of an analog of a positive number for matrices, is one way to think about it. Anyway, so those are some nice properties that we should remember for our autocovariance function. Now, going forward, what we also have is the idea of an autocorrelation function. And the autocorrelation, which I'm going to denote as rho of st, the Greek letter rho, is going to just be the normalized autocovariance. So we do what we would normally do, which is we will take our autocovariance and we'll divide by the respective variances, which is just the autocovariance at the same time point. It looks something like this. There we are. So this is just the autocorrelation. This is going to show up a lot when we start looking at actual time series data, because we like to know, well, are there correlations in time, right? If there are no correlations, then it looks a lot like a white noise process, assuming there's nothing sort of nonlinear going on there. But typically what we'll be doing is we'll be using the autocorrelation function, or an estimated version of an estimate of the autocorrelation, in order to determine kind of what type of stochastic or what type of time series process we have here and what we're dealing with. So let's go back and do another example. So in the last class, we had an example with the AR1 process. So this is going to be a slightly more advanced example. We're going to do an AR1 with drift. as I mentioned, we're going to use the AR1 as our standard example because it more or less tells us all we need to know, and adding more terms like a second order AR2 or 3 or whatnot is just going to make everything more tedious to compute. All right, so let's consider the AR1 process with drift. So what we have is we have an xt, which is going to be some a, the drift term, a constant, plus theta x t, minus 1. We want to go into the past, not into the future. Xt minus 1 plus wt, I'll say 4, wt weak white noise, WWN for weak white noise, with the variance of WT being sigma squared. So we can always strengthen that to independent or white noise if we really wanted to, but we'll just deal with it being uncorrelated for the moment. I don't think it's going to cause any trouble for this example. Anyway, yeah, so like we did last time, we can again use the definition recursively, much like we did in the last lecture when we were trying to write the AR1 process as a linear process. But now what we're going to do is we will do this recursively and use this to help understand, first of all, write it as a linear process, but then also be able to estimate two things. We want to estimate the mean and we want to estimate the auto-covariance, or I guess we're not estimating it in this case because we're not using data. We're going to compute it explicitly in some ideal setting. Right? I should reserve the word estimation for when we're actually trying to compute something from data. So make sure I'm precise about all this. Anyway, if we apply this definition recursively, well, what happens? Well, we still have an a here, but then when we apply the same definition to xt minus 1, we get another a. Then we get another theta with an xt minus 2, and we get a wt minus 1, and we add to that wt minus 1, or sorry, just wt. Right. And then when we move the terms around, we're going to get something that's going to look like a times 1 plus theta, and then we're going to get a plus theta squared x to the t minus 2, and then we're going to get a wt plus a theta wt minus 1. All right, so you can imagine what's happening here if we repeat this, ... If we repeat this, let's say m times, then what we get is, well, we get our a, and then we're going to have the sum from 1 all the way up to theta to the m, right? So that's the first bit. The second bit is going to be just theta to the m, xt minus m. And then the third bit's going to be the sum of a bunch of white noise pieces. So we're going to take j from 0 to m, and we're going to multiply that by theta to the j wt minus j for our sum going backwards here. All right, so where can we go from here? Well, we can extend this into the infinite past if we assume that in some ideal mathematical setting that this process can extend into the past indefinitely. Then what I'll say is basically taking m to infinity, which is going backwards in the past to minus infinity, with the absolute value of theta being less than 1, because otherwise our geometric series will not converge. We get that xt can be written as, well, what happens when we take this geometric series 1 plus theta squared plus theta, so on? Well, that just becomes 1 over 1 minus theta. So we end up with an a divided by 1 minus theta. Great. That second term, again, just vanishes because we have that theta is going to be less than 1. And as we multiply it by itself again and again and again, it sort of kills off that term. So we don't need that theta to the m xt minus m. I guess if we want to be more precise about it, we can compute it as a random variable and look at the variance as we take m to infinity and show that the variance disappears and the whole thing goes to 0. Lastly, what else do we have? Yes, we also have this infinite sum of white noise from 0 to infinity, which is going to look a lot like what we had in the last lecture, Wt minus j. So now we have this in the form of a linear process. Linear process form. Okay, and this is going to allow us to compute the mean and the autocovariance pretty fast. So first, the mean. So if we want to compute the expected value of xt, well, we just note that the first piece here is constant. So we just get an a1 minus theta. And the second piece here, that's the first piece. The second piece is just going to be 0, right? Because what we're doing is we're taking the expected value of white noise, and the expected value is 0. So it just becomes 0. Now, again, if we want to make this slightly more mathematically precise than taking the expectation of an infinite sum, we can take the expectation of the finite sum and then take that index to infinity. And that will give us kind of the idea of what's happening to this expectation. But here we can kind of just hand wave past that and say, it's mean 0. So the mean is just going to be this piece, which is quite neat. It means what? It means that I guess the mean is going to be dependent on two pieces, the a, which is going to be the drift term, but it's also going to depend on that auto regressive piece, theta. So if theta is very close to 1, this mean is going to blow up. If theta is very close to 0, it's not going to change very much. And then furthermore, we can actually look at the autocovariance, which is perhaps a more interesting calculation. If we were to compute the autocovariance for this process, what we end up with is something that's going to look like this. Well, we're just computing the covariance at time s and at time t, which again would be kind of annoying at first, but because of this recursive definition, or this using the recursive definition to write it as a linear process, things become a little bit nicer. So first of all, we have to subtract the mean when we do the covariance, which we just computed in the last step. And what we're left with is just the product of two infinite sums, j from 0 to infinity, of theta j w s minus j, and, well, I guess the exact same thing, kind of, except at time t. The sum j from 0 to infinity of theta to the j wt minus j. All right. Well, when we have a double sum or a product of two sums, we can write this as the product of all the terms. Again, if you're okay doing that for infinite sums, but everything's convergent, we assume that theta is less than 1, so it's all good to go mathematically. Regardless, now we're going to sum over I and j from 0 to infinity, and we're going to get two pieces. We're going to have a theta j and a theta I, and then we're going to have a w s minus j, a wt minus I. Okay, so now, well, we have a lot of terms in this summation to deal with, but luckily, most of them are going to be 0, right? Because expectation is linear, so we can bring it inside that summation. And when we take the expected value of the product of these two w's, basically the expected value of, we'll say w s minus j and w t minus I, it's always going to be 0 if the indices differ from each other. So in this case, if we have this only, I'll just write it out. We end up with a sigma squared, but we get an indicator function that says that s minus j has to equal t minus I. Otherwise, by the fact that these are uncorrelated, this expectation would be 0. So that's kind of neat, because that means when we put all of this stuff back together, well, what happens? Well, first we have a sigma squared in front of everything. Now our double sum, I guess, will become a single sum, because we're only summing up the terms where those indexes actually equal one another. And what do we get? Well, what we get is something like, I probably shouldn't skip a step. Okay, we'll do it in 2 steps just to make sure that I don't mess this up or confuse everyone. So what we'll have here is theta I plus j, and we have this indicator function, which I can actually rewrite, because again, it's just saying s minus j is equal to t minus I. So if I rewrite this, what I get is s minus t is equal to j minus I guess. If I got that right. Yes, yeah, that looks good. Okay, and then the reason why I want to do that is because I want to extract a theta to the s minus t, if that makes sense. So actually, why don't we do this in the side margin to make sure I don't make a mistake, and that you can also follow the calculations that I'm doing. So what do we have here? Well, we have that, what do I want? In this exponent here, I have an I plus j. Well, what I can do is I can write that as a j minus I, okay, but then I also have to add on to it, I think, 2I. Is that what I want? Let's say 2I, something like that. Mainly because I want to take this and replace it. I think I did this slightly backwards than how I did it in my notes, but that's okay. I can replace this with s minus t plus 2I. So when I put this all together, I end up with a theta to the s minus t and a sum of j from 0 to infinity of now theta, or I should say I, sorry, of 2I to the 2ith power. Yes, because all the other terms cancel out, and we're only left in the case where s minus t is equal to j minus I to make this all work out nicely. And we can write this out as an infinite series. Well, it's a geometric series, and when we put it all together, we get something that's going to look like this. All right, so let's take a moment to look at that before we go on further. Okay, so where were we? Well, here what we have is the result of our auto-covariance function. Now, there's one thing that I realized that I made a mistake when I did this the first time, when I worked through this just now. And that's that I forgot to put absolute values in. Because remember, our auto-covariance function should be symmetric. I should be able to flip the order of s and t. And what I was supposed to get, here I will write it in blue, is an absolute value around the s and t. So that one goes there, that one goes there. So where in the world did that come from, or where did that get lost? Well, that got lost from the fact that I have to consider, where is it, the indicator function in the opposite way as well, which is a weird sentence. If we take this indicator function here, maybe I shouldn't use green because I'm going to conflict with the other green. This is also the same as kind of t minus s being I minus j. So I have to consider sort of the reverse implication there as well. But everything follows here. It just means that we have to remember that our answer is an autocovariance function, and that means it needs to be symmetric in the argument, or else we missed something. Anyway, what does this mean? Therefore, let's just write it out here. K x st, the autocovariance of our AR1 process with a, I guess, a drift term to it, or a constant term there, is going to look something like this: 1 minus theta squared. Therefore, the variance of xt is just going to be sigma squared divided by 1 minus theta squared. All right. And there's something that I wanted to point out here. Note that t is not in this equation. So that is actually going to be really important when we talk about stationarity. That here we have a variance, and the variance does not depend on t. So we had this for the white noise process. We said we define a white noise process to have constant variance, but we never said that an AR process has to have constant variance, or an MA process has to have constant variance. All we did was say that the white noise does. But when we compute the autocovariance here, what we see is that the variance at time t has nothing to do with t. It's always the same, which is great. So that means that the mean, if we go back up here to the top, we have a couple things. We have that the mean is constant for all t, and we have that the variance is constant for all t. And that is going to be a really nice property that we're going to discuss in a minute. But before we do that, I just want to say a quick word on cross correlation or cross covariance. So before we talk about the idea of stationarity, let's write down the cross covariance. And basically the idea is that for two time series processes, let's say xt and yt, we can consider the cross covariance, which is going to look something like kxy, let's say st, which is just going to be the covariance of process x at time s and process y at time t. So in some sense, there's nothing too profound going on here, but it is good to write down this definition. And even more so, the cross correlation is going to be rho xy st. Which is going to be our cross covariance normalized by the respective variances in the denominator. In my lecture notes, I don't have a square root here, but I suspect I need a square root. So I'm going to put it in and double check later to make sure I'm not making a mistake while I'm doing this. But I did mess up the t though. Should be S and TT. because I should be dividing by the square root of the product of the variances, not just the product of the variances. So I'll have to make a note to change that in my notes. So the cross correlation is going to be important. And it's something like I mentioned with the autocorrelation, we're going to want to try to estimate it for two different sets of time series data. A textbook example that we looked at last year considers the price of oil, a barrel of oil, and the price of gasoline at the gas pump. And you might be interested in how these two time series are correlated, specifically at various offsets. So you could have the same time, t and t, but you could also have the time t and s being offset from each other. And that's going to make a difference in how you compute this and what it tells us, right? If there's a correlation, but if the correlation is offset in time, it's going to be called a lag, but we haven't gotten there yet. We're going to get there later. So as usual, I'm kind of running ahead of myself. But before we look into actually how to use things like cross covariance, we have to talk about stationarity, and this is going to be a really key concept for time series. Stationarity. Right, so the idea is that this is, roughly speaking, invariance to shifts in time. And like oftentimes in math, we have different definitions like weak stationarity and strong stationarity. So let's start with the idea of weak stationarity. Weak stationarity. So a weakly stationary process is going to be an xt such that, well, two things. The mean is invariant to time shifts. That is, that x, or the expected value of xt, is going to equal the expected value at xt plus r, which is just going to be some fixed value mu, and this is for all r. So the mean at some time is going to equal the mean at any other time, or it could be behind it, it could be ahead of it. The point is that the mean does not depend on the specific time, much like we saw in the example we just did. And we're going to apply the same thing to the auto-covariance. In this case, what we're going to say is that the auto-covariant at time s and t is going to equal the auto-covariant at time s plus r and t plus r. So in this case, what we're saying is not that the auto-covariant always equals one value, but that the auto-covariance between times s and t will be the same as if I take times s and t and I shift them forward or I shift them back, but keep them the same distance apart. And then the auto-covariance will be the same. So this is weak stationarity. This is the definition that we'll be using mostly throughout this course, but there is a way to strengthen it to strong stationarity. And strong stationarity basically is the same thing, an xt process, such that now we're going to use that same thing that I've written multiple times for any finite collection of time points, collection of times t1 through tk, then the distribution function the joint distribution function f of x at t1 through x at tk is going to equal the distribution at x t1 plus r through x tk plus r. So here this is the CDF function, the cumulative distribution function. So if I take, and I guess I can define it just to make sure we all remember what that is, that f of x t1 through x tk is just going to be the probability that x t, I guess I should define it for a little, well, we'll just do it like this, is less than or equal to some little x 1, and the joint probability of that all the way up to tk being less than or equal to some x k. Okay, so the definition is a little bit imprecise, but the idea is that if we have a finite collection of time points, we now have a multivariate random vector, and that multivariate random vector will have a corresponding joint distribution function. And what we can ask is, if we take that joint distribution, or we take that vector and we shift it in time, does the distribution function change? If it doesn't change, then we have a strongly stationary process. Again, this is a little bit stronger than what we will be using in this course. Typically, we just need a weakly stationary process, which means that the mean and the autocovariance, sort of the first and second moments, are invariant to time shifts. And oftentimes, we actually are faced with non-stationary processes and non-stationary time series, and we have to modify them in certain ways to make them stationary so that we can work with them. And I'll talk about that in a second, after another sip of tea. So the idea, and we'll talk about this, of course, more when you do estimation, but I'll say that stationarity is important for statistics, because if we want to, say, estimate the mean of xt, we don't want that mean to be changing the mean to change. Right? If we're trying to estimate, a mean, what would we do? We'd take a sample average. We'd add up all the points and we'd divide by the total. That's assuming that all the points are independent of each other. Here we have some dependency. We can still do that, but it only makes sense if every point has the same mean. If one t has one mean and another t has a different mean, then if we start trying to average them all together, we can't estimate them all the different means. Instead, we have to assume stationarity or transform a time series to make it stationary, so that when we say take a sample average, we're actually estimating the same mean for every time point. So that's one of the reasons why we need stationarity in statistics, is that we actually want to estimate things, and we want to make sure the things we're estimating are not changing in time, or else things become quite a big headache. So also, a weak, or strong for that matter, but specifically a weak or strong stationary process has a nice auto-covariance. And what do I mean by that? We already said that the auto-covariance is invariant to time shifts, but what that means is that let's sort of follow this through. If I have an auto-covariance function like this at times s and t, then, well, what I can do is I can shift both points backwards in time t units. So this, by definition of stationarity, is going to be s minus t and t minus t, which is just going to be s minus t and 0. And what this means is that we can actually rewrite this as just a single index tau, where tau is the difference between two time points, or in the language of time series, tau is a lag. So the idea here is that if the time series is stationary, then the autocovariance is only a function of the difference between the two time points. So I kind of mentioned this above, that doesn't matter where s and t fall. All that matters is that s and t are the same distance apart from each other, and that's going to give us our autocovariance. So if your process is stationary, you should be able to find an autocovariance function that has a nice form in terms of just t. Or tau, I mean, the difference between s and t. Also, I guess another also, the autocovariance is, I guess, both symmetric and bounded. Both symmetric and bounded. Okay, so why is that true? So for symmetry, well, what we have is that kx at lag tau is the same as adding and subtracting some time t from that. So we can have tau plus t minus t. So all I'm doing is adding and subtracting t here. But if we go back to the definition of autocovariance, we can do this at two time points, tau plus t and just t. Okay, so now we've reverted from the lag definition to just the regular definition. And then we can flip the order. So if we flip the order using the symmetry of the autocovariance, we get something that looks like this. And then if we cram it back together using the definition of stationarity, we get a t minus tau plus t. And what this means is that we have a minus tau. Cool. So what that means is that here we have that the autocovariance is symmetric about 0, in the sense that the autocovariance at a positive lag is going to equal the same at the same value as it would at the equivalent negative lag. So that's nice. And furthermore, we can show that it actually is bounded. That is, it can't just, the autocovariance can't blow up. It actually, in some sense, has to shrink. I mean, I guess if you're in certain cases, it won't shrink completely, but we'll look at lots of different examples of autocovariance. It's one of the main things we're going to do in this course is compute autocovariances. Right, so what are we doing? Well, first we note that kx at lag 0 is just the variance of the process for any time t. For any t, because it's stationary, we don't, any t is going to give us the same variance. We'll say then, by Cauchy-Schwarz, which is, of course, everyone's one of the favorite inequalities that you get to use in mathematics, and super useful whenever you're dealing with covariances, variances, and the like, because it's all just inner products in disguise. What we have here is that kx at 0 which is our squared variance, right? We can write that as the variance at time t and the variance at time t plus r. Remember, it's stationary, so these two variances are the same thing, no matter what index I shove in there. Then, thanks to Cauchy-Schwarz, we can lower bound that by the covariance between xt and xt plus r squared, which is going to be kx, the auto covariance at lag r squared. Therefore, we have that kx at lag, I guess I'll use r just to keep with the notation, is, well, in absolute value will be, I can erase this, is always going to be less than or equal to, it should be probably strictly less than, or else some weird stuff's going to happen, but we'll just say less than or equal to, based on this proof, then kx at 0, which also has to be finite, or else you're going to have infinite variance, and that's no good. We don't want infinite variance. All right. T's almost out, but that's okay. We can keep pushing through, because I want to do another example to try to show exactly what's going on here. So let's do another example. In this case, what we're going to do is consider one time series that's coming from a different time series. Actually, we're going to stop for 1 second, and I'm going to get something else to... Oh, wait, no, I got this. Never mind, I got something to drink. Got a helpful boost of caffeine. Right, let's do this. Let's consider a time series xt, which is a constant bit, a plus bt. There's no stochastics in there. It's just a linear, it's a line, right? It's a plus bt, it's just a line. And we're going to add some other time series to it, yt. With yt being mean 0 and stationary. So what I'm kind of showing is that we can take a stationary process and we can kind of modify it by adding other terms. So yt is stationary, it has mean 0. Now we're going to add a line to it. So instead of the process just sort of wiggling along, now it's going to follow some line in a sense. So what do we have? Well, we have that the mean, so the expected value of xt is just going to be a plus bt. And because there's a t in here, this is not stationary. So it turns out that if we take the if we add on this deterministic piece to our stationary time series y, we get a non-stationary time series x. But we can write xt minus a minus bt as stationary, which is, okay, just y. But the point is that we might observe xt in real data. Now, we don't know what y is. That's kind of hidden in the data. But what we can do is we can take xt and we can say, we have a stationary piece and we have a non-stationary piece, a deterministic piece. And if we remove the deterministic piece, what we're left with is just a stationary piece. And then we can do statistics on the stationary piece, right? So that's the kind of the intuition that we're going to be looking for as we go forward in this course. And yeah, we have one more thing to talk about, which is joint stationarity, and then we'll move a little bit into estimation. So joint stationarity, stationarity. There we have it. So for, let's say, xt and yt, if they are both individually stationary, so we need both of the processes to be stationary on their own, and also we look at the cross correlation or cross covariance function S and T, and we note that if it's equal to itself when we add R to both time points. So this is just the extension. This is for all R. This is just the extension of the definition to of stationarity to joint stationarity for two time series holding together. And all it's saying is that our cross correlation will similarly be invariant to time shifts. So there's nothing too much going on here except for more annoying notation than we had before. All right, we're going to take quick camera break, and then we're going to do the last, say, 20 minutes, and we're going to discuss the estimation of the mean and possibly the estimation of the autocovariance, because the next thing I want to talk about is the idea of estimation in time series. So the idea is that, well, first, what are we doing in stats? Well, if we have a time series, we probably want to estimate the mean. We might want to estimate the autocovariance. So what happens when we do that in a time series context, and how does it differ from when we would do that in a non-time series or maybe a classical stats 101 type setting where everything's independent? So let's try and consider that. So first, we're going to do the mean. So what we do is let xt for t from, I guess we want 1 to capital T, let's say, be a time series. I guess we want, more precisely, a weakly stationary time series. Otherwise, it's not going to get us what we want. Again, we need the mean to be the same at every point so that we can actually estimate it. Then, right, what we get is that the expected value of xt is just going to be mu. Okay, well, that's cool. So then what we want to do is we want to estimate mu somehow. So how do we do that? Well, we take the sample average. We do exactly what you would think to do in regular stats. So we consider the sample average, which is going to be mu hat, and that's going to be 1 over capital T, and the sum of just, well, I guess I'll index by little t from 1 to capital T of xt. All right, so we're just going to take it, right? This is really just x bar. The only difference is that now we think that the x's might be dependent on each other in some way, rather than in classical stats where we assume that all the x's are independent of each other. So how does that change things? Well, first, let's make sure that this estimator is unbiased. So to do that, we would take the expected value of our x bar, and we find out that that's just 1 over t times the sum, I from 1 to capital T, of the expected value of our xi's, and sure enough, this is just going to be mu. So yeah, we have a good unbiased estimator, but let's consider the variance, okay? So first, let's forget about time series and try to do a IID classical stats setting. So in stats 101, when the XTs are IID, we have what? Well, we have that the variance of X bar is going to be the variance of 1 over T sum of the XIs, or XTs, sorry. And because of independence, the variance of the sum is going to be the sum of the variances. So what we end up with is 1 over T squared sum of the variances of the XT. And this is just going to be 1 over T squared times T times, let's say, sigma squared, if sigma squared is the variance. And we find that we get sigma squared divided by T. So in classical stats, and if we do things like the central limit theorem or the law of large numbers, we know that the variance of the sample mean shrinks in terms of the sample size. So as the sample size, in this case, capital T, gets bigger, the variance gets smaller. Okay, so let's do that in our context. In time series, things change a bit. The variance of X bar is still going to be the same thing as before. It's the variance of 1 over T times the sum of the XT. But now we can't swap the variance and the sum, because the variance of the sum is no longer the sum of the variances. Instead, we have to consider all covariances present. So what happens is we actually get a 1 over T squared, and now we sum T from 1 to T, but we also sum S from 1 to T, and we have to sum up all the covariances of X T and X S. So things have become slightly more complicated. But the covariance at 2 different time points is just going to be our autocovariance. So we can actually rewrite this guy inside here as the autocovariance Kx at time T and time S. And actually, we can go one step further because it's stationary. So by stationarity, we can actually just write this as the absolute value of the difference between T and S. All right, so now we're making some progress, because what we can actually do now is sum this in a triangular diagonal sense. Okay, so what in the world am I talking about? Well, what I mean is that this sum is over T squared terms. And the terms in this sum, if we write them out as a big matrix, let's just say little t from, not 0, from 1 to capital T, and S from 1 to capital T, then what the terms are going to look like, right? It's going to be Kx at 0 all the way down the diagonal. And on the off diagonals, it's going to be Kx1 all the way down, and so on, all the way out to Kx, I guess in this case, it's going to be T minus 1, which is running outside my matrix, but that's okay. And then it's going to be symmetric. So similarly, on the lower triangular part of this matrix, we're going to have a Kx1, etc., all the way down. So what it means is that we're not really summing T squared distinct terms. In fact, we have the same terms appearing over and over again in the sum. And if we kind of squint at this and try to figure out how to solve it, what we get is that the variance of our sample mean is in fact going to just be, well, if we take the main diagonal here, we get t copies of k at 0. So when we divide by t squared, we end up with a kx0 divided by t. All right, but we're not done yet because we have all these other terms, and these other terms, well, it's a little, I'll just write down the answer and then we'll look at it. So we're going to get a 2. We're going to get a 2 because we have the upper triangle piece and the lower triangle piece. So we actually have each term appearing in 2 diagonals. And then we're going to sum, in this case, I'm going to use z as my index from 1 to t minus 1, which is going to be the lag. The lag is going from 1 to t minus 1 as we move along the diagonals of this matrix I wrote here. And what we're going to get on the inside of the summation is 1 minus z divided by capital T, k, x at lag z, right? So you can kind of stare at this formula and see that it makes sense with respect to the matrix that I wrote down. So for example, if we look at z being 1, well, what happens? I'll just put it down here. For z equal to 1, what we're doing is we're summing, we sum, or we have, let's just say, we have, well, how many kx1s do we have? We have, I guess, t minus 1 times 2. We have 2 times t minus 1 kx1s that we have to add together. And then when we divide, then divide by t squared to get, well, 2 over t and 1 minus 1 over t times kx1. If I take the 1t and divide the 2 by it, and take the other t and divide the thing in the parentheses by it. So this here kind of coincides with what we see in the summation up there. So again, we can kind of use that to double check to make sure that formula makes sense. But what we wanted to point out is that, let's say, noting that kx0 is just the variance, sigma squared, we have that the variance of x bar is going to be sigma squared divided by t, the same thing we would have got in Stats 101, but then we also have this other crazy bit which is coming out of the lags. T minus 1, 1 minus z divided by t, k, x, z. All right. So this is the IID answer, and this is the correlation piece. And what this means is that the variance of our sample average is going to be inflated based on the autocovariances that we see in our process. So that will change the variance of our estimator. Okay, so that's how things are modified now when we're dealing with time series. And yeah, I think we will just stop this lecture right here. And then in the next lecture, we'll start up with the idea of how do we estimate autocovariance, and then how do we detect white noise? Because ultimately, we're going to want to understand what type of a time series we have. Is it a white noise process? That's a really good thing to know. So we're going to want to figure out how to detect that. And we're going to look at things like the estimated correlation and the estimated autocovariance, which is going to be really important for telling us what type of time series we have in our real data. So I will squeeze that into the beginning of next lecture, and then we'll move into some more. It'll be a good way to start before we get into chapter 2 of my notes, where we do more proper time series statistics. So I'll see you in that lecture when I record it.